is induced in national earthquakes forecasting.
Thank you, Thorsten and Luc, for the nice introduction. I really appreciate the opportunity to visit Austin. It was high time for me to come here. That's my first time. And I've had a wonderful time discussing with all of you. I hope you will have some good time listening to the talk. You'll tell me at the end. So I'm going to talk about earthquake forecasting. It's a topic that we've been working in my group over the last 10 years. And the work I'm going to show is the work that was done mostly by students on postdoc working in my group. So I've been careful not to use the term earthquake prediction in my title, and the reason is that letter that that is posted at the entrance of the conference room of the Seismo Lab at Caltech. I read it. So this was written by Benno Gutenberg. This laboratory does not predict the earthquakes. Specific predictions giving time and place come from amateurs, publicity seekers, believers in the occult, or just plain fools. So you'll tell me at the end of the talk what you think. So this is the definition of earthquake forecasting that was put forward by the International Commission on Earthquake Forecasting in 2011. I think it's a good definition, and that's really what we mean by earthquake forecasting. Honestly, we could call that earthquake prediction as well, but the essential point is that it's probabilistic. So I read it. An earthquake forecasting model is a systematic method for calculating the probabilities of target events within future space, time, and domain. So what we are trying to calculate is that quantity that you have here at the bottom of the slide, the probability of having an earthquake larger, at least one event larger than a magnitude n, over a certain time window starting at t, from t to delta t, and within a certain area or volume of the crust represented by A. That's really what we are after. So if this quantity is depending on time, we have a time dependent earthquake forecasting method, and if it's independent of time, it depends only on the duration of the time window. It's a time independent hazard assessment that is done. These notions will come up later on. So keep in mind what we are trying to do is not forecasting individual events, is forecasting the rate of events, from that the probability of having magnitude larger than something. So the roadmap for the talk. So I will remind you some basic notions of earthquake phenology and fault mechanics. Then I will explain the principle behind earthquake forecasting based on physics. You will see that there are elements that are not entirely based on physics. There are still elements that are phenomenological. And then we'll talk about applications to induce seismicity. I will finish the talk with a digression about where we might go when it comes to trying to predict individual events in a natural setting. So let's take the example of the Gorka earthquake. I'd like to talk about this example because I've worked a lot in the Himalaya in the past. So, and we have a lot of details on that particular earthquake, on the setting, in particular because we deployed the seismic network way before the earthquake, so we have more than 20 years of local monitoring of seismicity, and also GPS stations. So we knew about the deformation before the earthquake, the co-seismic or the post-seismic deformation. So here, this map is showing the result of the red shading was obtained by inverting geodetic displacement measured before the earthquake over something like 10 years of measurement. And what you see from this data is that the fault that is running at the front of the Himalaya at the surface, so it's coming at the surface here, is locked from the surface to a depth of about 15, 20 kilometers over a width that is about 100 kilometers. So that's pretty clear from the geodetic measurements. The black dots in the background represent that the earthquakes that were recorded there before the Gorka earthquake, and you see that most of the earthquakes occur at the down deep edge of the locked fault zone, which is well explained. This is the area where you have stress buildup, right? This area is locked, and deeper here beneath the high Himalaya and Tibet, you have a ductile shear zone, and you have stress buildup at the transition from the creeping zone to the lock zone. The Gorka earthquake started as one of those earthquakes. It's the same actually the epicenter is somewhere here at the western edge of the rupture. It's represented, oh yeah, I should point at the screen, sorry. So the earthquake started here at the western end of the rupture and propagated in that direction. So it started just like one of these smaller earthquakes that were recorded before. It was just a little bigger. And when I say a little bigger, it's a 7.8 earthquake. But you see that it's still not the kind of earthquake that will unzip the entire locked fault zone. So you can tell that this fault must produce much larger earthquake than this 7.8. Right? And we know that because the fault here at the surface is slipping at 2 centimeters per year, which is the shortening across the Himalaya. And we know from trenching that we've had events with of the order of 5 to 10 meters of slip in single ruptures. So we know that much larger events can happen. So the Gorka earthquake is well documented with the high-rate GPS stations that were deployed in that area. Here is an example of a recording from one station, which is just north of the rupture. So the 0 here is the time of the initiation of the earthquake at the epicenter, and you can see that at this station, which is just north of Kathmandu, nothing happens for about 30-40 seconds. This is the time for the rupture to reach that point. And then let's look at the north-south component. The station moves south by nearly 2 meters in about 10 seconds, okay, and then it stays locked. So the rupture pass that point and then propagate away, and you can tell that it's a crack rupture from the inversion of those data. So here on this animation, this is the slip rate on the interface inverted from the high rate GPS data, and you see actually the rupture propagating eastward from the epicenter to Kathmandu and beyond Kathmandu. So this earthquake is just one of the earthquakes that are happening in the interseismic period that grows a little bigger than the average earthquake. And of course, the question we would like to be able to answer is, what's the probability of having earthquake that will rupture the entire locked zone? And that's where, I mean, we have some difficulties, and I will come to that later. The thing we can say about these ruptures that are rupturing the entire locked fault zone up to the surface is that they must return with a period of about 1,000 years, and the moment of such ruptures is of the order of 8.5 to maybe 8.7, right? So that's a requirement to close the moment budget, so that the strain that is the deficit of strain that is accumulating because the fault is locked is released by the earthquake. So we can do that same kind of simple logic. So let's now, so we've seen what happened during one earthquake. Let's now say what we can tell about the population of earthquake itself. So as you know, when an earthquake happens, it's going to trigger aftershocks, and you can analyze the seismicity catalog by plotting the distance in time and in space between successive events. This is a plot that was popularized quite a lot by Zalyapin and Bain Zion. And if you do such a plot and take a seismicity catalog from Nepal, California, whatever, you will typically see a bimodal distribution with a cluster of events that are close in time and space. These are the aftershocks. And then you have another cluster of events that are farther away, and those events are actually the background earthquake, the earthquake that are not triggered by previous earthquake, that are triggered by tectonic loading. And when you look at the interval distribution of those earthquakes, they follow an exponential decay, they follow the expectation from a Poisson process. This is what is shown here. So this population represents earthquakes that are triggered by tectonic loading. They are independent from each other, and they are mostly memoryless. They don't know about the time of the previous earthquake because this population is dominated by smaller earthquakes. The aftershocks, they follow the typical Amory law. So this is the cumulative number of earthquakes after a main shock. You have an increase as the log of time, which is, that means a decrease of the seismicity rate as 1/t. Okay, that's the other important phenomenological law when it comes to the time evolution of seismicity. Magnitude now. You are probably familiar with the Gutenberg-Richter distribution. So what is plotted here is the log of the number of earthquakes with magnitude above a certain value that is the abscissa here. Right? So in such a plot, generally what you see is a linear decay with magnitude, and the slope is called the B value. So to first order, it says that you have 10 times less earthquake of magnitude 7 than magnitude 6, because the B value is of the order of unity. So, so that's the Gutenberg-Richter distribution. And the great value of that magnitude frequency distribution for earthquake forecasting is that if you want to forecast large earthquakes, the earthquakes that have a risk to cause damages, you can do it based on the rate of smaller earthquakes, right? Because the ratio of the two is more or less constant as long as this distribution is verified. On the smaller earthquakes, you can collect them with a good seismic network with a low detection threshold over a small period of time. So one point that I won't go into much detail is that this distribution has to be bounded, because you cannot release more energy with earthquake than there is incoming energy due to tectonic loading. And so this distribution has to be bounded. There is a debate about the shape of the tail of the distribution. Is it tapered? Is it truncated? But somehow it has to end at some maximum magnitude. So let's now talk about how we calculate the probability of having an earthquake larger than a certain magnitude. So based on the Gutenberg-Richter distribution, if over a certain period of time you have observed a certain number of earthquakes, you can use the Gutenberg-Richter distribution to calculate what is the maximum magnitude earthquake that should have been observed for that period of time. And that's simply the intercept with unity. Okay? So you draw that line, and that gives you a magnitude. That's the expected magnitude from the Gutenberg-Richter distribution. So now the earthquake catalog is the realization if we forget about the aftershocks. We look at the population of independent events. They are, you can draw them from a Poisson distribution, a point process distribution, which is memoryless. And so if you expect a certain number, if you know the rate of the process, of the Poisson process, then there will be fluctuation in the number of earthquakes you are going to observe due to the stochasticity of the Poisson process. So the number of earthquakes is going to be variable, and that will determine the probability of that distribution moving away from the expected blue line, which would be the distribution for an infinite catalog. So without going into the detail of that, you can calculate the probability of moving away from that distribution. So you can calculate the probability of having an earthquake larger than a certain magnitude, taking into account the Poisson process. And this is all analytical and simple. So all you need to know is the rate of the Poisson process and the B value. Then you can take into account uncertainties on the estimate of the rate, uncertainties on the estimate of the B value, and you can calculate the expected magnitude frequency distribution and the confidence level on this distribution. From there, you can actually go all the way to what is going to be important for seismic hazard assessment. You can calculate the probability of observing an earthquake larger than a certain magnitude. So you could pick 3.5, for example, as a function of time, and that probability will take into account the fact that it's a Poisson process, on the uncertainties, on the on the b-value, for example. Okay, so in the end, to calculate that probability that I mentioned earlier, all you need is a model of earthquake in time and space. So that's the A value of the Gutenberg Richter. How many small earthquakes, let's say magnitude 0, you're going to have in a certain time window and in a certain area. And then you need to assume a magnitude frequency distribution. For example, you can assume the Gutenberg Richter distribution with a translation as at a maximum value M max. So now, to do seismic hazard assessment, probabilistic seismic hazard assessment, we have to evaluate the rate of earthquake, represented by A, which may vary in space and time, how the b-value is eventually changing in space and time. I won't talk about that because to first order, b-value doesn't vary much, right? So in the talk today, we're going to assume that the b-value is constant. And we need to estimate the shape of the magnitude distribution, what's happening at the tail, for example, M max. So the question is, how do these quantities vary in space and in time? So to address that question, you can start with a simple earthquake machine. Mine is simpler than the one that Chas has built here. So this is my earthquake machine operated by my daughters some years back. So let's play it. So that's the simplest model of the earthquake cycle that you can come up. Well, you have two bricks here. You pull with an elastic, right, and you turn the crank. And so at some point the shear stress carried by the elastic will exceed the resistance to sliding due to friction, right? And you get an earthquake, and the house card collapsed. And so this is the simplest model you can think of, in which we represent the sliding process by a friction loop. Okay, so according to this very simple model, if in isolation of any external factors, what you would get is a periodic behavior. If you turn the crank at a constant rate, the stress increases, and then you reach the condition for failure, and then the stress increases, and you get the condition for failure, and then it will repeat. What you get from that is that the rate of earthquake is proportional to the stressing rate, the rate at which you're turning the crank. That's all that comes into that. That's the simplest model you can think of. Okay, so in reality, the instability, the frictional instability, is going to depend on the shear stress and on the normal stress. In the previous experiment, you remove the one brick, for example, then you reduce the resistance to sliding, you reduce the normal stress, and then you will have smaller events that will repeat more frequently. Actually, will be twice as frequent. So we know from rock mechanics that we can represent the condition for frictional sliding by the Coulomb criterion, which is represented by this blue line here. This is the shear stress, this is the normal stress. And so if you have a point on the fault that is at this initial state, you change the stress by a certain quantity. So delta tau will be the change in shear stress. Delta tau star is the change of normal stress. You bring that point here, and so what matters is the component toward the failure that gives you the probability that failure is going to occur. So that vector is proportional to the change of shear stress minus friction time the change of effective normal stress. Effective normal stress is normal stress minus pressure. So this is the criterion that is traditionally used to model, for example, aftershocks, or to model the probability of bringing a fault to failure. We know that this criterion works quite well to explain, for example, the spatial distribution of aftershocks. I mean, here I'm showing a figure from Rothstein and Jeff King of aftershocks due to the Landers earthquake. So you have the rupture in black here, The color shading is showing the change of Coulomb stress. Red is positive, so you bring the faults closer to failure. Blue is negative, and you see that the aftershocks fall mostly in areas of increased Coulomb stress. So we know that that criterion does quite well at explaining where earthquakes are happening. So now if you combine the Coulomb stress with that simple model where the friction drops from a static value to a dynamic value, what you expect is that the seismicity rate R relative to the background seismicity rate, the seismicity rate at constant tectonic loading, is dependent on the stress rate, the Coulomb stress rate, divided by some normalization Coulomb stress rate, which is actually the stress rate at which tectonic loading is occurring. Okay, that's the simplest model you can think of. So with this simple model, now if you imagine that you have a sudden increase of the stress rate, and you have a ramp increase of the stress applied to a population of fault, with this simple model, you should have a boxcar response of the seismicity rate. The seismicity rate should increase instantaneously and should be constant, as the stressing rate is constant. And when you remove that perturbation, it should drop back to the background seismicity rate instantaneously. Okay, so let's see how this simple model, which assumes instantaneous nucleation of earthquake, can be used. Here, this is an application to the India-Asia collision zone. You have the seismicity observed over 10 years, simply from the International Seismic Catalog. And here you have the strain rate, the horizontal strain rate. So it's second invariant of the horizontal strain rate tensor, calculated from geodetic measurement. I'm not showing the geodetic measurement, but there is enough that you can produce a relatively good strain rate model. So you see intense stress buildup at the front of the Himalaya, and you see a few other faults. This is the Altintak fault, this is the Kunlun fault, I1 fault, and so on. So you do see some faults popping up in this strain rate path. So one thing that you can do is test that the seismicity is proportional to the stressing rate. So all you do is that you count the number of earthquakes in each bin of strain rate. So we have cut here the range of strain rate we have here into 10 bins, and we calculate the number of earthquakes in each bin. Actually, you can plot the magnitude frequency distribution of earthquake in each strain rate bin. And when you do that, you get a very nice distribution. So red corresponds to the earthquake happening at the highest strain rate, blue at the lowest strain rate, and you see that the distributions are just offset with respect to each other. So the B value is nearly constant. The slope is always the same, but the A value, the rate of earthquake, is increasing. And if you plot the A value as a function of the strain rate, which is this plot, it's nearly a linear function. Okay? So the seismicity rate is, to first order, proportional to the strain rate. So the medium, you can consider it's elastic, and so then it's proportional to the stress rate, as you would expect. Okay, so that's the way you can do time-independent seismic hazard assessment. You can do it this way. You start from this map. You calculate then the rate of earthquake of small earthquake, and then you calculate the expected or the probability of an earthquake reaching a magnitude over something using the equations that I've described earlier. And from there, you can calculate a hazard map like this one, where you add one element, which is the ground motion prediction, GMP, ground motion prediction equation, so which is relating the ground motion at one point to the location of the source and the magnitude of the source. So from there you can get actually the probability of the PGA, the ping ground acceleration, exceeding a certain value that is plotted here at 10% probability in 50 years. Okay? And this is what the engineers will use typically to design buildings, right? That's what goes into a building code. So the advantage of the logic I've just followed compared with more traditional technique is that it's all, you have a very clean stream flow going from GPS to this thing. You don't have logic trees, and so it's relatively clean and simple. So now, how do we move to time-dependent forecasting? Then this is very important for induced seismicity, because if you use that formalism for induced seismicity, you would find, I was talking with Alexandros earlier this morning, you would find that the hazard in Texas now is larger than what it is in California, which is probably not exactly right. So you have to take into account the time dependence of the process. So now we're going to talk about how we can do it. So one element that you take into account is that the nucleation process is not instantaneous. We know it's not instantaneous because if it were instantaneous, we would see a strong correlation between earthquake and solid earth types. And we don't see that. So it's an indication that the stress changes that are of the order of tens of kilopascal, up to 10 kilopascal, due to the interaction with the sun and the moon, don't drive detectable variation of seismicity. But that tells you that the earthquake don't respond instantaneously. There's the nucleation process that takes time. So here you can use friction laws that were established in the lab. So this is famous work done by Dietrich, and one of the simplest formalism that you can come up with to explain the laboratory measurement and that result in the time-dependent nucleation process is this rate-on state formalism that was introduced by Dietrich and Greenwald, Jim Rice, and so on. So here you have friction that depends on the log of the sliding velocity and the log of a variable theta here, and this variable theta here varies with the sliding velocity. So you have two coupled equations here. That might seem complicated, but actually it's not. So there are two important elements. Here, a fault creeps all the time with this friction law, but it's a logarithmic dependence, so it creeps at very, very low rates during the interseismic period, and when there's a slip event, it goes to instability. The second element is that theta here is here to account for healing. It's going to account for the fact that when you have a slip event, then you restore strength on the fault. This is called healing. So this equation is essential if you want to have a seismic cycle. If you use a friction law that doesn't have healing, then you cannot get a seismic cycle. Okay? And when you solve this equation to look at what is the slip rate for a spring and slider system, the same system I showed earlier, as a function of time, what you see is that the fault is slipping all the time, but it accelerates towards an instability. And at some point you declare you have an earthquake where typically the slip rate is faster than 1 centimeter per second. Okay? So, but you have a time-dependent nucleation process resulting from this rate-on-state friction law. So now imagine that you have a fault that is initially slipping at this slipping velocity. This is log scale, and you load it at constant rate. It's going to produce an earthquake, an instability at a certain time. If you apply a change of Coulomb stress on that fault, you're going to actually shift the time of the earthquake by just shifting that branch. So let's say that you augment the stress to that level. You can calculate the new velocity based on this equation. You are now here, and then you follow the same branch as this one, but it's been offset here. And so the earthquake is going to happen earlier. If you have an increase of Coulomb stress, you advance the time of the next earthquake. If you take a fault that was actually sliding at a much lower velocity, so you have the same process, but because of the shape of that curve, the time advance is way larger. Okay? So for the same increase of Coulomb stress, you're going to have a much larger time advance because that you're shifting that branch to here, and so if you look at the difference between that time and that time, it's much larger than the difference between that time and that time. Okay? And you can calculate that easily. Okay, so yes, so this is a population of faults now that will produce a constant rate of seismicity if loaded at a constant rate. If we apply a sudden Coulomb stress change on that population, suddenly we don't have any more a constant rate, you get aftershocks, and you get the 1/t decay of the seismicity rate. And this prediction of this equation, actually, of this formalism is a reason for its success, that it explains very nicely the Omori decay of aftershocks after a large earthquake. The fact that the rate of earthquake decay has 1/t. Okay, so which might not be the only explanation for it, but it's one very plausible explanation. So this is the formalism that we use in our modeling. And there's one element that we added to what Dietrich had done before, is that most of the time earthquakes are induced at places that are not tectonically active. And so it could be that your population was not being loaded at a constant rate to get started. So you can imagine that those faults were created, in the past, and then the system is quiet for tens, hundreds of million years, and then you reload the system by perturbation, which might be a fluid injection, extraction of gas, or whatever. So when you revisit the derivation that was proposed by Dietrich in 94, and you do the math, you come up with this equation now, where the seismicity rate divided by the background rate is some exponential function of the change in Coulomb stress minus a threshold. And here you have an integral that will cause the 1/t decay. So one important element here is the threshold, is the stress, the minimum stress you need to apply to start restarting the seismicity. So there's a threshold that comes naturally from this analysis. The other property of this equation is that now you don't have a step increase of seismicity because of the nucleation process. So here we're looking again at the response of a population of fault to a ramp increase of stress. So first you have a delay that is due to that threshold. You need to bring the population to rupture. And then you have a smooth increase of seismicity. That's the effect of the nucleation process. And when you stop actually perturbating the population, then it's going to decay as 1/t. That's the Omori law. That results again from the nucleation process. So let's now look how this formalism works when we apply that to induced seismicity. So here we are looking at earthquakes that were triggered by gas extraction from the Groningen gas field in the Netherlands. So here you have the footprint of the gas field. On top you have subsidence that was recorded from GPS leveling in SAR over the gas field. The ground has subsided by up to 50 centimeters over a few decades. And here the gas is extracted from a formation, a sandstone formation about 200 meters thick at a depth of about 3 kilometers. This is the cumulated volume of gas extracted as a function of time from the gas field. And you see that at the beginning, nothing happened. There was no earthquakes. Here you have the cumulative number of earthquakes. The earthquakes started to be observed only in the 90s. The subsidence was observed from the beginning. Okay? And the subsidence is simply because the pressure is dropping in the reservoir, and so the ground above the depressurized reservoir is going down. One detail that I will come up later is that here in blue, this is the rate of extraction. So it's the derivative of the cumulative volume extracted. It varies seasonally. They pump more gas in the winter. That's where they need to heat their homes. And you will see that it's an important element in the story. So now we have to explain the lag. But you'll probably guess that it has to do with this threshold that I introduced earlier. And we need also to explain the fact that during that period of time, the extraction rate was constant, but the seismicity rate was increasing exponentially. Okay? So, and that's where actually, when I was contacted by the operators to see if we would be interested in working on that problem, and it turned out to be a gold mine for earthquake science. So let me describe the workflow that we have developed to actually model the seismicity. So we have three elements in this workflow. One is the reservoir model. So we calculate the pore pressure in the reservoir at depth. as a function of the location of the wells, the pressure at the wells, and the flow rate at the wells. So this is, I would say, traditional reservoir modeling. We had to simplify the big thing so that you could calculate that on a laptop and do MCMC simulations and so on. But that's one element. So the reservoir flow model is informed by the pressure and flow rate. Then from that you can calculate the geomechanics, how much compaction you get of the reservoir for a given drop of pressure. That geomechanical model is informed by the surface deformation measurement, the subsidence that you see at the surface. And the critical quantity is the compressibility. I will explain in a minute what it is. Then, based on this geomechanical model, you can calculate not only surface displacement, but stress changes in the subsurface. You can calculate Coulomb stress changes. And then you're going to feed that to the equations I just showed, that is relating the seismicity rate to the Coulomb stress changes. You then calibrate the parameters of this equation from the observed seismicity. And then you can use that model to validate. You take half the catalog and you verify that it works well for the second half. And you can use it to do forecasting in the future. If you know the plan of operation, how much they're going to extract from the various well, you can make a forecast of the seismicity. So the reservoir model, I don't go over the detail, it's just to show how the model fits the observations. The color dots are the pressure as a function of time. The pressure drop is quite significant, of the order of up to 30 megapascal. So it's a very significant pressure drop in the ground, and our model fits pretty well the observation. So we think we have a good hand on the reservoir model. So the reservoir is bounded by aquifers. The aquifers are penetrating a little bit in the aquifers, so it buffers a little bit the pressure drop, but that effect is very small, and it is taken into account in the modeling. So the next step is I pushed the wrong button. The next step is the geomechanics. So for the geomechanics, we represent the reservoir by cuboids, and we calculate the deformation and the stress changes using semi-analytical equations. So it's a little similar to Ocala for shear displacement on a fault. So it's based on the theory of a nucleus of strain in an elastic medium. It's just that it makes everything semi-analytical. It's an integral function of an analytical function, and you just need to integrate based on the corners of the cuboids. Very efficient numerically. The parameter that's going to be critical here is the compressibility, the ratio of the compaction, so delta H over H, the change in thickness divided by the thickness of the reservoir, divided by the pressure drop, delta P. That's going to determine the subsidence, and that's going to determine the deformation around the reservoir. So we use the geodetic data for the calibration of the geomechanical model. So we have INSAR measurement, we have GPS leveling. We do a blind source separation of all those data together to extract the signal that is clearly related to the reservoir. You may know that when you look at INSAR data, you have tropospheric effect. I mean, there's quite some noise and so on. So this is a way to clean up the data. So when you do that, you find two clean components over that area. One is the surface subsidence over the reservoir. This is the spatial distribution of that component, and this is the temporal evolution of that component. And you have another component that actually we didn't expect, we didn't know it was there, but it turned out to be useful. There's a small reservoir here that they use for temporary storage. So, when they have too much gas, they put it back in that reservoir, and then they use it when there is high demand. So this one has a purely seasonal pattern. There is no trend, and it shows very nicely from this blind separation technique. Okay, so now you need to calibrate the compressibility. So the compressibility, you get it from so you use this analytical solution from Kuvshinov to relate the subsidence to the compaction of the reservoir. So now you have delta H. We know H from seismic profile, so we know what is the thickness of the reservoir. and we know delta P from the reservoir model. Okay? So here, what is shown here is the ground subsidence over that small reservoir when they do seasonal storage. And you see that the ground displacement is very seasonal. So the color coding is showing the measurement from INSAR or GPS. The thick line is the prediction of the model. Once you calibrate this compressibility, it's one parameter that you change. Okay? So you estimate the compressibility. This is one quantity for that reservoir. It's so small that you don't see heterogeneity of compressibility. You can do the same thing for the entire reservoir, and then you have variation of compressibility by nearly a factor of 10. That depends on the facies of the sandstone or something like that. So that's going to create heterogeneities of compaction that will create then deformation of the overburden that will actually help drive the earthquakes. So heterogeneities of compressibility is going to help drive shear deformation of the overburden. I should say, if all the medium above the reservoir was subsiding by the same quantity, if it were all homogeneous, the pressure drop homogeneous, the reservoir concentric, nothing would happen except at the edge. There would be no deformation. You would have a rigid block, no drop above the reservoir. You don't have that because of compressibility varying in space, but also because the reservoir is highly faulted. So when you look at the seismic images from the reservoir, you see a lot of normal faults which are plotted here, which are offsetting the reservoir. So what's going to happen now is that if you have compaction of the reservoir on both sides of that fault, it's going to drive shear fault on that fault. So it's just like a transform fault between two ridges in plate tectonics, right? So you have shear strain building on those faults. And so now if you calculate Coulomb shear changes in the subsurface around the reservoir, you can see that where the reservoir is offset by fault, you have stress concentration. Okay. So now you calculate Coulomb stress over the whole area, and because of all those faults, you have Coulomb stress changes nearly everywhere. So you can explain why the seismicity doesn't occur only at the edges of the system, but actually within the system. So next thing is that you calibrate now the seismicity model. You determine the four parameters of the seismicity model to fit the time evolution of the seismicity. So we use the equation that I introduced earlier, and here is a fit in space. So this is the observed seismicity rate, this is the predicted seismicity rate, and here is the fit in time. So we've cut the catalog in two. We use the first half to determine the model parameters and the uncertainties on the parameters using the Bayesian inversion. And then we forecast for the second half. So the blue curve is showing the number of earthquakes that are observed every year at Groningen. So these are the observations. There is fluctuation from one year to the other. This is essentially because of the Poisson process. And the cyan is the prediction of the model, and the red line shows the variability due to the uncertainty on the model parameters. So this is the prediction of the best fitting model, ignoring the Poisson process. If you account for the Poisson process, this is the range of variation you should get at the 90% confidence level. Okay? So you can see here that the model fits very well the period used for training, but it does fit very well also the period used for validation. And the uncertainty range actually overestimates the variability of the seismicity which is expected, but I won't go into that. Okay. How do we validate the nucleation process? Because we have now estimate of the parameters, and it predicts a certain time for the earthquake to nucleate. So just looking at the time evolution over many years is very difficult to really validate the nucleation process. One thing you can do is look at how the seismicity rate is responding to this annual fluctuation of stress due to the seasonal production of gas. So what is plotted here is the variation of stress at the depth of the earthquakes due to seasonal production. And you have variation peak to peak of the order of 10 megapascals, so it's of the order of times. It's very significant, in fact. And if earthquakes were instantaneously triggered, they should follow exactly the change in the stressing rate. And actually, you can calculate what should be the fluctuation. So let me introduce now a plot that was actually introduced by Schuster in the 19th century. He was interested in the problem of earthquakes related to lunar tides. And the plot works this way. You go around the clock in 1 year, and each time you have an earthquake, you make a step in the direction corresponding to the time of the earthquake. If the earthquakes are distributed uniformly over the year, after 1 year, you go back to the origin. Okay, so if you go to look at n number of years, you should go back to the origin. If there's a seasonal variation of seismicity, you're going to have a drift from the origin. The time of the maximum rate of earthquake will be the time you read on the clock here. And you can calculate the probability of shifting at the observed distance from the origin due to a Poisson process. So what you see here is that this is the observed seismicity at Groningen. It has a very clear seasonal pattern. This is its maximum in mid-March, right? And the probability that it occurs by chance is less than 0.01%. Okay, so we can exclude that it's just the randomness of the Poisson process. There's a real seasonality. Then you can calculate what you would expect from a Poisson process. If it were a Poisson process, you should have a much stronger response to the seasonality change. These are random realizations of a Poisson process driven by the Coulomb stress tension, assuming that the earthquakes are instantaneous. You see that you don't get the right amplitude and you don't get the right phase. The earthquake rate should be maximum in January, when it's colder, when they are pumping the gas faster. With our nucleation model, here you have random realization of our process in blue compared with the observation. You see that we get the right phase, the right amplitude. If you calibrate the model without the seasonal variation, which is the game we played here, then actually, if you ignore that there are seasonal variation in reality, then you don't calibrate well the model. The forecasts are all over the place, and you cannot explain the seasonality that is observed in the catalog. So it's a strong proof that nucleation is time dependent, and that actually the formalism rate onset friction does quite well at explaining that. A quick note on Oklahoma, just to show that the same formalism that was demonstrated here in the context of gas extraction works also for earthquake induced by injection of wastewater. So here you have the time evolution of the volume, of the rate of injection of wastewater in green. And here this is the seismicity rate in Oklahoma. So you see that there is a shift. 2 years, it's not decades. On the previous plot for Groningen, it took nearly 30 years to get the first earthquake. Here they were more brutal at injecting the wastewater, and so they got the earthquake earlier, in about 2 years. You see a very rapid increase of seismicity, and because it was relatively rapid, that it helps actually calibrating the model. So now the earthquakes are happening in the basement. I didn't say it, but in Groningen it's mostly in the cap rock. Here they are in the basement, but here is the fit to the time evolution of the seismicity. So same thing, you take a fraction of the catalog to do the calibration, you take another part to do the validation, and it works pretty well. And this is the comparison in space at different times. So here up 2002, up 2015, and 2024. So it's the exact same framework that I introduced in the context of injection of fluid water. When you look at the model parameters we get for Oklahoma, it's actually very similar to what we have at Groningen. Here there's one parameter that we invert using the seismicity, the permeability. Because contrary to Groningen, where we had the pressure and the flow rate are all the wells, we could do the permeability determination based on those data. Here we don't, so actually you can use the seismicity pattern to invert for the permeability as well. Okay, so now I've shown that we can forecast pretty well the distribution of seismicity in space in the natural context. We've seen the case of the India-Asia collision zone. We've seen also that that same formalism works quite well for induced earthquakes, provided that you introduce the threshold that tells you that the faults were eventually away from criticality to get started on the nucleation process. So we can do quite well in forecasting the seismicity rate in time and space. What about forecasting events? So far we said it's a Poisson process with aftershocks. Okay? But really, is the Poisson process satisfying? For large earthquakes, it's certainly not satisfying, right? There must be a memory effect. In the simple model I was showing at the beginning, the spring and slider system, you need to turn the crank up to a certain point to create a new earthquake. It's periodic, it's far from a Poisson process. Even if you have several of these systems interacting, it's going to create more complexity, but there will still be a memory effect. So let's see if we can, how far we are from actually introducing a memory effect so that we replace this Poisson process by something that will be more mechanistic. So I'm going to take the example here of Sumatra. This is work that was done by Jean-Philippe, which was a student at Caltech working with Kerry and myself using coral data. So we have a pretty good record of ruptures over several centuries from the coral data. I won't go into that technique, but believe me, and you can talk to Luc, I know he's interested in that topic as well. And we also, you can use the coral data on the GPS to determine the locking pattern. So, long story short, the fault is locked from the trench to the island of Sumatra. So, similar context to the Himalaya. And once in a while it produces an earthquake. So, that same area that is locked in the interseismic period produce repeating earthquake. But when you look at the slip distribution during those various earthquakes, they are very different. That same patch is producing sometime 8.3 with the peak slip in the north. Sometimes the peak slip is farther south. So you see a lot of variability. There's nothing systematic. And that's the latest earthquake that is way better constrained than previous earthquake because we have GPS seismology and so on. So this is the time evolution of the slip potency deficit, so you can see that as the average stress on the fault as a function of time. So here the fault is being loaded for a long period of time. We go from 1520 to 1700. Oh, first earthquake. So you have the first earthquake that happened in the south. Second earthquake, another one. So you see that pattern, but you see it's very different from when we were turning the crank with the spring and slider system. We have a cluster of large events. Okay? And then it's going to be quiet until 1700. So we have a problem here that the same patch doesn't produce always the same earthquake. So we would like to be able to reproduce this variability in the rupture and the clustering between events. Right? There's a clustering in time here. So to look at that problem, we actually focused on a system that is a bit simpler. So we looked at slow slip event in Cascadia because we have long time series with a lot of events. Even Sumatra is a little too short to go very far into that analysis. So I'm showing here slow slip event in Sumatra. Here you have the time series of slip on the plate interface at one point in the north, and here this is at a point in the south. So you see that it shows the kind of complexity that we've seen at Sumatra. Maybe not as spectacular as what I've just shown, but it's not the periodic pattern that you get from turning the crank of a spring slider system at a constant rate. It is more complicated. So some years back, Adriano Gualendi has done some analysis of that system and demonstrated that you have a strange attractor, so it's a chaotic system, but with some predictability. It looks like you have a horizon of predictability of the order of 2 weeks. Okay. So what we did is we designed a numerical experiment. This is just to show the kind of variability of the ruptures that we see here. So this is time, this is latitude, and each time you have an earthquake here. Yeah. I'm going over time, sorry. I'm nearly done. And so here we are using a numerical model that produces earthquake very similar to those slow events. You might recognize things that look like the Gorka earthquake. They are just much slower, very small stress drop. The variability we get in that system is very similar by design to what we have in Sumatra, in Cascadia. So these are the ruptures, this is time. And so it's very chaotic and so similar to what we have in Cascadia. So the interesting thing here is that you can predict the earthquake pretty well in that numerical system based on knowing only the slip rate on the fault at one particular time. So the test that is done here is that we assume that we know slip rate on the fault as a function of time, and this is as a function of distance along the fault. So if we know the slip rate we take 16 points. So it's undersampled. It's not very fine sampling. So we take 15 points at a given time. We know the slip rate, and then we say, can we predict the time and the location of the next earthquake? Actually, we can do it. We can do it simply because the stress is going to be self-organized in that system. Each time there's an earthquake, it redistributes the stress in the neighbors, and so there's a correlation between the stress at one point and the stress at another point. And that creates a memory effect, and the stress translates into a slip rate because of right-hand state friction. This is based on right-hand state friction. So if you know the slip rate, you have an information on the stress, and because the stress is correlated by the cycle, you actually can do a forecast. So here, this is showing the observed rupture in the numerical simulation.